is the health course, now that's surprising. Now, I don't think chemistry is boring per se. Actually, I think it's really interesting, only when you get to understand what is going on between atoms. Now, I don't mean chemical reactions such as magnesium reacting with hydrochloric acid to produce hydrogen gas bubbles. No, I mean what is going on at the subatomic level. For example, intermolecular forces and the specific energy required to bond two atoms. Now that's interesting. And that's important because we can then understand the way that molecules bond and their characteristics, which is important in developing drugs, creating medicine, and maybe even finding a cure for a modern incurable disease. Except we don't do that at Kernel Lab, or any other chemistry course for that matter, because how the hell are we supposed to see to the subatomic level? I mean, scientists can't even do that. In fact, no one has actually ever seen an atom before. Well, you might think a computer could do that, right? I mean, that's what computers do. You take an input into an algorithm, and it is guaranteed to give you an output. Well, sorry to say that there is no algorithm for a computer to calculate this energy level. Actually, let me rephrase that. There is no algorithm for a classical computer to find this energy level. Why? Let's put it this way. Chemistry is something that happens in nature. Atoms bond, it's natural, and there's not really a why to why it happens. But in a computer, they read information using bits, a 1 or a 0, or an on and an off of electrical pulses. Now, these bits behave in such a way that just can't simulate the way that nature functions, and hence they can't find the energy level required to bond two atoms. So here's a thought. Instead of using classical bits, why not use some other fundamental unit that can simulate the way that nature functions? Something found in nature itself. In all honesty, nature is quantum mechanical, whether we like it or not. So why not combine quantum physics and computers? Computer plus quantum physics? Quantum computers. You know, a few months ago, I didn't even know my laptop sitting at home could be categorized into something called the classical computer. So the difference between a classical and a quantum computer is that classical computers calculate things that we already know, just faster than the human brain can process. We can also compare a classical computer to things we already know, such as this classical ground, or this classical board, or even my classical hand. Now, a quantum computer, on the other hand, calculates things we don't know, because it can measure quantum physics that happen at a nanometer, where we have no idea what is going on at that level, because things are just so small. So a quantum computer can measure things we don't already know. Or it can complete classical computations just at an exponentially faster speed than classical computers. So other than this, there are three things that classical computers have that quantum computers have that classical computers don't. And that is qubits, superposition, and entanglement. Now qubits are like bits, not in the way they behave, but in what they represent, and that is reading information. So unlike classical bits, qubits can be an electron, a photon, or any other subatomic particle, because again, it could behave the way that nature behaves. Now, what really allows qubits to be much more faster and much more powerful than classical computers are superposition and entanglement. And this allows quantum computers to calculate things such as optimization or prime factorization, aka things that classical computers really suck at. Maybe that's why theoretically, 300 qubits can map out the entire universe starting from the Big Bang. For some reference, it takes 16 bits for a classical computer to read a color. So as mentioned before, a classical bit can be a 1 or 0 or an on and off, however you prefer to call it. The point is, classical bits only come in two states. Now, a qubit in superposition, it could be a 1 or a 0 or everything in between. So in quantum mechanical terms, a 1 is a spin up and a 0 is a spin down. And spins are essentially the position of the qubit in relation relation to the magnetic field it is lying on. So if we compare a classical bit to a coin, its states would be heads or tails. Now for a qubit, if we compare that to a coin, its state would be, well, the coin spinning. Spinning. This allows quantum computers to be much more powerful than classical computers. For example, if I wanted to double the computational power of a classical computer, I have to double the amount of total bits. So a 256-bit computer is twice as powerful as a 128-bit computer. However, for a quantum computer, I only need to add one more qubit. So an 8-qubit quantum computer is twice the computational power of a 7-bit quantum computer. So a superposition can be represented anywhere on this block sphere, where the north is the spin up and the south is the spin down. This means that qubits in superposition have infinite states. However, if you actually wanted to measure the state of a qubit, how would you do that? Because its states are infinite. Well, you have to decide that you want to measure its state by perhaps probing it with some light or interacting it with the environment, and only then can it fall into a classical state. So if we take our coin analogy, it would be the qubit in superposition would be it spinning, and once you decide that you want to measure it, it would be your hand stopping the coin from spinning until it falls into either a heads or a tails. So in a quantum computer, things happen instantaneously. That's entanglement. It describes the behavior of qubits who behave in relation to each other because qubits become entangled when they somehow interact physically. Einstein called this spooky action at a distance because it seemed as if qubits were communicating with each other faster than the speed of light. For example, if I measured the state of a qubit here, its entangled qubit, which could be at the end of the universe for all I care, would have the opposite state no matter what. That's just how the universe worked in terms of quantum physics. This allows quantum computers to be much more faster than classical computers because entangled qubits behave in relation to each other, no matter how far away they are, or if there was some barrier or obstacle between them. They behave faster than the speed of light. So back onto my whole chemistry dilemma. It turns out there is a quantum algorithm that can determine the energy levels of two atoms bonding. And that's called the variational quantum eigensolver, as seen by this orange line over here. Now, this orange line is so precise that it covers the exact energy represented by the blue line. In fact, it only has a 0.6% uncertainty error. So this algorithm solves a question of optimization by finding the minimum eigenvalue of a matrix. In simple terms, a matrix is a rectangular array of values that pertain to an equation, and an eigenvalue are values that satisfy this equation. So by finding the minimum eigenvalue produced by this matrix, the algorithm can find the energy required to bond two atoms. So if we do that, then we would computationally understand atoms, and then we can build atoms and molecules in our own labs. And this is revolutionary because we can discover drugs, build medicine, and even find cures for diseases and illnesses such as Alzheimer's, everything. So, will a quantum computer ever replace our classical computers? No, because classical computers and quantum computers have calculations that are done with the same efficiency. But a quantum computer will revolutionize industries such as healthcare and chemistry with optimization, and with encryption and banking with prime factorization, and many other big unknowns in our society today. So again, will a quantum computer replace a classical computer? Never. You can keep your Mac laptops, but is the quantum computer a better and more sophisticated computer? Hell yeah. Except it is much, much uglier. Thank you.